Well, thank you very much for that question. So yes, we are a process licensor, so I'm going to try to give you some perspective on what we do. And what we do is that we develop technology and we transfer those technology to project developers here in Turkey so that they can develop their own project based on technology that we will have fully de-risked. And this is something that we have been doing the last 50 years to de-risk the technology so that can be transferred to clients to build those plants. So today I will focus, and we have been doing that mainly in the refining and petrochemical industry, but the last 20 years we have also developed a lot of technology for the sustainable plastics. And when it's come to sustainable plastics, there are multiple solutions. There are a combination of bioplastic, recycled plastic, chemical recycling plastic, and I'm not going to address all of them in just 10 minutes. It's just not possible. My message is there to tell you today that those routes exist. They are routes, and what you can see on those slides are some of those technologies that we are already licensing to clients, and they are technology to convert biomass into chemicals so that you can produce new plastic. There are technologies that you can produce some bioethylene. There are different and multiple technology available in the market, and that you can reintegrate into the steam crackers, into the aromatic complex to produce those low-carbon polymers. What I'm going to address mainly today on those 10 minutes is recycling, chemical recycling as a complementarity of plastic. Also, I wanted to add one slide, which is even more busy. I will not go into that slide, but this is a slide about CO2. Today, there are a lot of technology and discussion around producing low-carbon fuel, sustainable aviation fuel. Be aware that through those routes, which are capturing CO2, converting the CO2 or combining the CO2 with hydrogen to produce synthetic fuels, you are also able to produce some feedstock for steam crackers to produce some low-carbon polymers. It's even more the future, but the technology are there. And just a week ago, there was an announcement for a project in Norway for Braskem using some of those synthetic naphtha to produce low-carbon polymers. So again, adding some complexity on the top of it, there are technology available today for bioplastic, low-carbon plastic, and also circular plastic when it's come to chemical recycling, which I'm going to focus now. What my message to you today is that those technologies which are going to complement mechanical recycling to meet the huge gap that you introduce, for example, for PPWR, they already exist. There are plants which are already in operation. For example, for pyrolysis, the pyrolysis of very difficult mixed plastic, contaminated, those technologies exist on the market and there are plants already in operation. That's just some pictures because I'm an engineer, so a picture worth thousands of words. So what I'm sharing on the screen are some pictures of plants which have been in operation since multiple years. So converting very difficult mixed plastic into an oil that can become new plastic to meet the challenging and huge gap that you are presenting in terms of demand to meet food contact application on polyolefin, they exist. But what you can also see in those slides is that the capacity is relatively small. If you look at those two plants which are operating in Spain since more than 10 years, they are only 4 KTA. Even the new one, which has just been commissioned and which is now in operation for Sabic in the Netherlands, in Geri, it's small. It's only 20 KTA. But technology is there. Technology is there, and it has demonstrated that it's work. So this is for pyrolysis. So this is just, again, a picture worth thousands of words. I made reference to the plant of Sabic of 20 KTA based on that TAC technology that we are licensing at AXENS. But there is also the coming plant of Total near Paris of 15 KTA feedstock, taking that very difficult plastic and turning into an oil that can be going further to steam cracker for production of new polyolefin. Of course, when you talk about pyrolysis, starting from a contaminated feedstock, you may guess that there are some contaminants that you will find on that plastic pyrolysis oil. Here again, the technology to clean and upgrade those pyrolysis oil do exist. I mean, I'm coming from the refining world. Maybe there are some people also coming from refinery in the room. They know that cleaning an oil is something that has been done since many years. There is a technology today available which is turning that pyrolysis oil coming from plastic waste or even from tires into a clean drop-in naphtha. So you can go from waste to a naphtha, which is equivalent to the quality of virgin naphtha, and process it in a steam cracker to produce new polyolefin. So those technologies, they exist. And, very important, as Ineos already pointed out, when you do that, it has to make sense in terms of life cycle analysis. It doesn't make sense to do such kind of chemical recycling if at the end the carbon impact of the polymer you are producing is higher than virgin. And we have done multiple life cycle analysis. In fact, our clients, the clients who are developing those projects, they are doing those LCA. And on all those LCA, based on converting that difficult to recycle plastic into an oil, cleaning that oil, going to a steam cracker, well, you are able to produce an oil which has got a lower CO2 impact than the oil which is coming from crude oil. And here in that example, I'm showing a number of 18%. It's not because it's done in a country where you have got green energy. No, 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 no. I mean, when you put on some conditions where you have access to nuclear green energy, the number is even lower. Here, 18%, this is, well, a mix of carbon intensity that you will find on projects in Eastern Europe, in some Asia countries. So you are able to produce an oil which has 18% less carbon when you are pyrolyzing that mixed plastic to produce new polymer. And I'm not taking incineration or waste to energy as end of life for that waste. If you do so, then the number is even higher. If you consider that your plastic is going to waste to energy, and instead of sending that plastic to waste to energy, you put it on those pyrolysis pathway to produce new plastic, the saving in terms of carbon per ton is, as you can see on that slide, nearly 3 tons of CO2 saving compared to incineration. So it really makes sense in terms of LCA to process that route. I'm saying that because many are seeing pyrolysis as an energy-intensive process. Yes, it has been in the past, but those continuous processes which have been developed, those plants which have been built by Total, Sabic, they really make sense in terms of LCA. So this is for the polyolefin. I wanted to touch also, as we have got experts from PET in the room, there are, as you rightly say, glycolysis is a way to go for depolymerization of PET, but you can go one step further in terms of purification to process a very difficult PET feedstock. When I say very difficult PET feedstock, I'm taking, for example, polyester textile, or multi-layers trays that contain also polyolefin, or color bottles with other labels. Well, there are technology to process that very difficult waste that cannot go to mechanical recycling because there are color contaminants. It's a mix of textile which contain polyester and some other resins. Well, there are technology to do the depolymerization, to do the cleaning, and go back to food contact application. Those plants, again, already exist. It's not as developed as pyrolysis, but the depolymerization and purification of difficult-to-recycle PET are technology which are now available in the market. And you can go from those difficult feedstock back to mineral bottle of water under a food contact application standard. So I'm going quick because I already have 10 minutes, but this is really the kind of feedstock, and the pictures that I'm showing you is one of those first plant, demonstration plant in Japan, which has been in operation since more than a year, and that we are using to process feedstock which are coming from multiple different parts of the world. Of course, the plastic waste feedstock in Europe is not the same as the one in Turkey, in Egypt, in India, in China. So we are using that facility to validate that the technology can take and process those feedstock together, packaging, but also textile. We are processing textile coming from Japan, from China in that unit, and demonstrate that you can go back to a clean, purified monomer to go back to textile or even mineral bottle of water. So my message was really to say, and this is just an example of a project which is under development. This is the message I wanted to share with you today. The technology is there. It's proven. The feedstock we see that on the client's project, the feedstock is there. Of course, there is always a need to prepare the feedstock. But in every country where we are doing study for our clients, we see that the feedstock at the end is available. We see that there is a positive impact on the environment. On all the LCA which are done by third-party companies, we see that they make sense in terms of LCA. The issue is that those projects are stuck. They are stuck on pre-FEED. Why are they stuck on pre-FEED? Because there is, as you say, some uncertainty on the way you are going to do the calculation under some of this legislation, the PPWR, the end-of-life vehicle, all those kind of regulations. So that's all the little bit our clients, when they see that there is still that ambiguity on how you are going to calculate. And the other aspect is the price to pay for those polymers. The condition driving the blend owners to buy the recycled plastic with the necessary premium are still missing today. This is what we see on most of the projects. Not tomorrow, because as you rightly say, well, you would not have any choice to use low-carbon polymers. But as of today, in December 2025, when you discuss with our clients, they have some difficulties to get off-take agreement from their clients to say, okay, I go. And we know that is going to change. And for us, it scares us a little bit because to build those plants that I was just showing you on the screen as example, it takes time. It takes 2 years. It takes 3 years. So to get to that point, I mean, developing, I'm not on the mechanical recycling business, but maybe to develop a mechanical recycling plant, you will need 1 year or 1.5 years. But really, for those chemical plants, you will need minimum 2 or 3 years. So the technology is there. The LCA makes sense. This is the last slide also to share that the solution will not be unique. You will have a mix of contribution of course, mechanical recycling, which will play the main role, then chemical recycling, and then bioplastic. And all together, you will be able to produce products which are 100% sustainable. But to get there, our clients, they need to have more visibility on the legislations. And what I see, and that was my message when I discussed with our client, is that they are struggling today to get, enough tech agreement from their clients to go ahead and develop those projects. So this is the message I wanted to share today.
Nicolas, thank you very much.